mean that atoms can stick together to form a molecule. So for example, this here is a molecule of CH4. It has 5 atoms altogether, and they're held together using these lines. So these lines are bonds within the molecule. Remember, this whole thing inside here is a molecule, and the lines represent bonds that hold the atoms within the molecule together. So these are bonds within the molecule. There's a word for meaning within molecule, and it looks like this. Intra, meaning within, intramolecular, meaning within a molecule. So these are intramolecular forces, these guys here. Okay, so that's what we've learned previously. But we must also consider the forces between molecules. So molecules generally tend to be in groups. So you don't just have one molecule in a container. If you've got a container full of a substance, there's many molecules there. So what holds them together? Well, there's got to be some type of force that attaches them even weakly or loosely that makes them interact with nearby molecules. Okay, so here is a second molecule of that substance, and the broken line between them represents another type of force. Now, it's not another bond. This is what we call it, or this is a force that's between the molecules. So force between the molecules. And there's another word for this. Now, it's kind of similar to the first one, so you've got to be careful. This is inter, which means between, molecular, so force between molecules, intermolecular forces. And intermolecular forces are really important because these are the things that have to be weakened or overcome when you're trying to make a substance change state, so maybe to boil, or they'll also need to be overcome if you want a substance to dissolve. So these intermolecular forces affect the properties of the substance. So what boiling point will they have? In other words, how much energy does it take to make these boil, to weaken these forces and make them boil? Also affects the properties whether they are soluble in another substance or not. And again, we'll see more on that detail later on. It's really important to remember that we do not break the covalent bonds. We do not break these when we boil something. We do not separate it into separate carbons and hydrogens. We do not do that. We just break the attraction between the molecules. So we eliminate or overcome these forces when we boil or melt something. That's really important. So there's different types of these intermolecular forces, and all of the intermolecular forces are pretty weak. They're much weaker than the actual solid line. So intermolecular forces are weaker. So these broken lines are always weaker than the solid lines and the bonds. But there's differences within different strengths of them. So there's different strength intermolecular forces, but they're all weaker than bonds, much weaker. Okay, so we're going to look at the weakest type of intermolecular force today. Okay, and these are another thing we've previously seen. Sorry, we'll just jump into something here. Say we've got a molecule made of H and Cl. We've learned that they create a polar bond and therefore a polar molecule. So for example here, chlorine will attract the electrons in the pair closer to itself, will lose out on its share of the electrons a little bit and become delta positive. So what we've done is we've shifted the share di, because there's two ends of this molecule now, a dipole. Okay. So some molecules have dipoles, so they have clear areas where there is more positive and more negative charge. And then you can pretty straightforwardly see how, okay, well, if you brought another one of them close, well, there might be some attraction between two dipoles. So say, for example, we brought another one of these molecules close. If you brought another one close, well, we can see how, if this one also has the same dipole, which it would do, that, hold on a second, now we've got two areas which are oppositely charged and might attract each other. Okay, I'm going to see that later on, but it's probably makes sense to show you that first, that some molecules are obvious why there's an attraction between them. But let's go, for example, to something like this, Cl, Cl. So here is a chlorine molecule, and they have equal electronegativities. So there's definitely not going to be any dipole here. Neither of them are attracting electrons closer to themselves than the other one. So there's not going to be any obvious areas of positive and negative charge. So when we bring it close to another chlorine molecule, how are they attracted to each other if there's no dipoles? Well, the answer is a little bit complex, but what you have to remember is that chlorines, or any atom, have lots of electrons moving around inside them. We've seen this before, electrons moving around in orbitals inside each of the atoms. Now, what we're going to do is we're just going to focus on one electron. Now, remember, there's loads of them doing this. So we're going to focus on one electron. I'm going to draw it here with an orange circle. Well, what we know about that is it never stays still. It's always moving. So 1 second, it's going to be over here. And it's going to be creating this tiny, for a fraction of a second, a slight delta negative on this right-hand side of the atom. Now, in a fraction of a second, it's going to be moved over to here. And now the negative dipole will be on this side. And what will it will have left behind? Oh, sorry. What it will have left behind, if I can get rid of this now where this electron isn't anymore, it will have left behind a slightly delta positive area, because now the nucleus is closer to this side and the negative electron is closer to this side. So technically you've got this very temporary dipole, but it's not, it's really weak, because a fraction of a second later, the electron will be back over here again, and it will have flipped, and the delta negative side will now be on the right again, and the delta positive side will be on the left. So we'll be back to delta negative here. So it's kind of a difficult concept, but the idea is that all of these electrons are constantly moving around. And when they do this, they create what we call temporary dipoles. They last for fractions of a second, temporary dipoles. And it's these temporary dipoles that can attract each other. So one molecule can, for a fraction of a second, have a delta negative at one end, and the other one can have a delta positive. And if you add up all of the electrons moving around, there's enough dipoles to just very weakly attract each other. These are the weakest type of intermolecular forces, and they have a funny name. They're called van der, and again, that's a second name, so they're named after somebody. They're called van der Waal, spelled with a W, not a V, van der Waal or van der Waal, if you like to try and pronounce it like that, so you'll remember how it's spelled, van der Waal forces. They are very weak forces of attraction, which explain how some molecules stick together. Now, every single molecule has at least these van der Waals forces. Some of them might have other intermolecular forces as well as these, but all molecules have electrons moving inside and therefore are going to have these temporary dipoles creating these van der Waals forces. So van der Waals forces exist for all molecules. Which molecules have only van der Waals forces? Well, we've seen up here that these molecules with dipoles in them, these are what we call polar molecules. So polar molecules have these up here, these types of forces, which are stronger than this one that we've been talking about, van der Waals. So polar molecules don't have just van der Waals, they also have this force. But these molecules here, these two Cls, each of these is what we call a non-polar molecule. They don't have poles. So non-polar molecules, van der Waals forces are the most important for them because that's all they have. So van der Waals forces are a type of intermolecular force. They're the weakest type. So if they're the weakest type, it's easy to overcome them. So most of these substances, non-polar covalent molecules, most of these substances will be gases at room temperature because their boiling points are really low, and they'll have low melting and boiling points. Okay, right. So that's van der Waals forces. What affects the strength of the van der Waals forces? Well, let me just point out for a second. Let me say here's another non-polar molecule, hydrogen. So H van der Waals interact. It will also have van der Waals forces with another non-polar molecule. They will also have van der Waals forces between them. So that there and that there are both van der Waals forces. The question is, well, which one is stronger? What affects the strength of van der Waals forces? Well, the hydrogen is going to have weaker van der Waals forces. So this here is weaker. And the reason for that is, remember what creates van der Waals forces? The movement of electrons inside the molecule, inside the atoms of the molecule. So whichever molecule has more electrons in the atoms, they're going to create more of these temporary dipoles. So it's the size of the atom and how many electrons are moving inside that makes stronger or weaker van der Waals forces. Now, I say stronger or weaker van der Waals forces. Still remember, though, that this is any van der Waals force is extremely weak. It's just that some of them are slightly stronger than others. There's a range within that, even though relatively they're weak compared to other forces. So this up here, what exists between two polar molecules is stronger than any van der Waals force. But van der Waals forces can also be stronger or weaker than each other. Okay, so it's an important concept. So we've got a little table for us to fill out over here. Okay, so this is something that we can work on together. So exists between which molecules? So remember, the heading here, if you're taking this down, is van der Waals forces. Van der Waals forces. Okay, all right. So exists between which molecules? So which molecules are the important for? So if you can remember that after my explanation, go ahead, pause the video and write down the answer now. We were. And where am I? Just here. Okay, so between which molecules? All right, so first of all, the important thing to note is that all molecules have van der Waals forces, all of them forces. But some molecules have only van der Waals forces, so these are really important for them. Which group of molecules are those? Pause the video now and write down the answer. These are really important for non-polar molecules, like the diatoms, H2, Cl2, okay, e.g. H2, Cl2. But there's also things like CH4, methane. Methane, even though there's carbon and hydrogen are not the same atoms, there's no dipoles in CH4. So overall, it's a non-polar molecule. Why do they arise? Okay, so again, can you explain that using a diagram that I've done before? If you think you can, pause the video and try it now. So you need a diagram and an explanation. Let's see if you can draw the diagram here where I explained it and explain it over here. Okay, so this is the diagram I'm talking about. Okay, so say the two chlorine molecules there, the van der Waals forces. So if you can, again, pause the video if you haven't done this already and draw the two chlorine molecules with the van der Waals force between. And if you want, for your own notes, you can compare it with two hydrogen molecules like I've done. What I would also do if I was you is kind of like what I did, show how electrons move around, creating temporary dipoles. So see what I've written here in orange, that there are temporary dipoles created as electrons move around. So remember, electrons have a negative charge, so whatever area they happen to be in at any particular time is going to be slightly delta negative, and in any area where they're not is going to be slightly more positive. So we've got these tiny, weak temporary dipoles. All right, so once you've drawn the diagram, we're back to the explanation. How do they arise? They arise from the movement of electrons. So moving electrons create temporary dipoles in two molecules attract each other. All right. Right. What factors affect the strength of van der Waals forces? So why would van der Waals forces in one molecule be stronger than in another molecule? So I used two chlorines versus two hydrogens to explain this. So if you can, pause the video there and talk about what factor affects the strength of van der Waals forces. Pause the video, do that now. Okay, so the key thing here is the number of electrons that are moving. Okay, so more moving electrons inside the temporary dipole. Okay, so more moving electrons means more temporary dipoles means stronger van der Waals forces. Okay, so first of all, thing to note out is that all molecules that have only van der Waals forces will all have low melting and boiling points. Low melts. That's not the full story. How does the strength of the van der Waals forces affect the melting point and boiling point? So obviously they all have relatively low melting and boiling points, but obviously then the stronger the van der Waals forces, remember this is controlled by how many electrons are moving inside the atoms, but they're all going to be low. Okay, they're all low, but within that there's a range. Okay, so bigger atoms, more electrons moving. If there's van der Waals forces is the only force, they're going to be all lower melting and boiling points. But the more or the stronger the van der Waals forces, it will make the boiling points and melting points be a little bit higher than ones with really weak van der Waals forces. Okay, so this stage we're ready to have a go at some questions. Okay, so the first thing here is it says state the factors that affects the strength of van der Waals forces. So put away the notes now that we just took up in the table above. We're just doing these practice questions. What is it that controls the strength of van der Waals forces? Pause the video, write that down. The next thing, Why are electrons responsible for van der Waals forces arising in molecules? Again, explain how do electrons cause van der Waals forces to arise. Pause the video, do that. You can use a diagram, try and do the diagram from memory to help you explain it if you want. Good. Okay, so you should only be playing now if you've done 154 and 155A. Let's look at 155B and C. It says, use the table to explain how the strength of intermolecular forces varies with the number of electrons in the molecules of the halogens. So here we have the halogens. Okay, this is group 7, and each of them is a diatom. So we've got F2, Cl2, BO2, and so on. Okay, and look at the melting points. At the top, the melting point is very, very low, and it rises as we go down the group. So melting point gets higher, and look, the same thing happens to the boiling point. Very, very low, increasing. Okay, so now if we think about the molecules, F2, Cl2, BO2, and think about what controls melting and boiling point, why do we see this pattern here? Why does the melting point and the boiling point increase as we go down the halogens? Okay, now it is to do with van der Waals forces, and it is to do with the strength of the van der Waals forces, but why are the strength of the van der Waals forces changing? So think about that. Pause the video, write it down. I'm going to go through the answer the next day in class. You should only be playing if you've done that now. Explain in terms of intramolecular forces present why fluorine. Okay, I'm pretty sure that's going to be wrong. Yeah, this should be intermolecular forces present. Why fluorine is a gas at room temperature, while bromine is a liquid at room temperature. Again, pause the video. Discuss why are those boiling points different. Last question, part D, explain why the FF bond in fluorine is a non-polar covalent bond. Little bit of revision. Why, if you've got two Fs like this, is it non-polar? Pause the video, write your answer. All right, guys, that's it for van der Waals forces, a really important concept because it decides and helps us to understand why melting points and boiling points are different from each other for different substances. In the next video, we're going to look at another type of intermolecular force. Okay, guys, we'll see you in the next one.